still on this idea of creating new graphs from other graphs, adding graphs together. So if you've got two different functions and you want to draw the picture of when they're added together, I think in physics they call this superpositioning of graphs, or some fancy title like that. But theoretically I could use the idea to draw x squared plus x. I mean, we know what it is, it's a parabola, we could do it other ways, but let's use it as an example. So I draw x squared, there's our parabola, and I draw y equals x. And I say, well look, I want to add these two graphs together. How do I approach it? There's key things to look at. So x and y intercepts are always important. Now, first thing I notice is both of these go through the origin. So clearly when I add them together, because we're really just adding the y values. Well, 0 plus 0 is 0. That's going to be an x and a y-intercept for that matter. The other x-intercepts, what I do, if I've actually got the picture, is I slide a ruler along. And all I'm looking for is when is it the same above and below? Because one would be negative, one would be positive. You'd add them together and you get 0. And I just read off my ruler and it might be, oh, look at that, they're both 1 centimetre above and below. That's the point I'd have an x-intercept. So roughly about there I reckon I've got it. Then I just draw in as many lines as I need. Well, in reality I don't draw the lines again, I'm just sliding my ruler and looking at the actual measurements. But let's imagine these are where, that's a great one to do, the point of intersection. And so I'd get my ruler and say, oh, that's about, I don't know, let's say it's 2 centimetres. So I add that together and I get, 4 centimetres, so I'm up there somewhere. But then I do as many points as I need. And I just slide along and mark them off. And so if I mark those points in, there we go, I start getting a picture. And I can see, oh, look at that, it is also a parabola as well. And then as many as I need, I go, okay, there's my graph. So that's the idea. Let's do it with this one. X plus 1 on x. Y equals x, y equals 1 on x. So x-intercepts and y-intercepts. Well, in this case, I have neither. Because whilst y equals x is going through the origin, it doesn't exist on the other one. So I haven't got a point to add it to. And then when I look at the others, well, over here on the right-hand side, they're both always positive, so they're never going to add together to give 0. And on the left-hand side, they're always negative. I'll plot some points. The point of intersection is a good one, so yep, let's add those together. I'll get twice as high. And I've got another point of intersection down there. Again, I just do as many as I need to get the shape, and we see what's happening. We get like a little, well, it's not a hyperbola, but these U shapes in between the two curves. End up with something like that. With something like this, keep in mind, those discontinuities. If it doesn't exist in the domain of one of the functions, it can't magically exist in the new function. So it's still not going to exist there. So my new curve, I still do not exist at x equals 0. That brings up an interesting point. See, I could get this graph, x plus 1 on x, and if I had to add it to the graph 1 minus 1 on x, well, if you add those two together, you get x plus 1. So you think, oh, I'm just going to draw the line y equals x plus 1. It's not the line y equals x plus 1 that I'm drawing. It's these two functions that I add together. And it wasn't in the domain. X equals 0 is not there. So it can't be in the domain of the new function. So yeah, I get y equals x plus 1, but at x equals 0 I get a point discontinuity. It can't magically go into this new function. A bit like what I was talking about the other day, that x on x one. Same sort of idea. And when we did the reciprocal graphs, wasn't in the domain of the original one, so it can't be in the domain of the new one. And that's what I was talking about. So the x-intercept, if one is positive, one is negative, so that's when I'm sliding my ruler along, then clearly that's where the x-intercept's going to be, because they'll add together and get 0. Symmetry, if you've got symmetric graphs, it will retain the symmetry. What do I mean by that? If you're adding an odd function with an odd function, then what you end up with should be an odd function. That's what we've got here, if you have a look at it. X plus 1 on x. Y on x is an odd function. 1 on x is an odd function. But look at the red curve. It also is an odd function. It has the rotational symmetry that we look for. And same thing would happen with an even function. If you add an even function with an even function, it would end up being an even function. It would retain the symmetry there. Odd plus even, you lose the symmetry. It won't be symmetric. there were ones like this in one of our exercises. So let's look at this idea in a bit more detail. How would I draw these two added together? Well, the critical points idea comes in really handy here. What's causing the problem is when the absolute value changes from positive to negative. So I look at those points. So negative 3 is a key point. What happens when x is less than negative 3? Well, if x is less than negative 3, think of any number you like that's less than negative 3 and sub in, see what happens. If I substitute it into x plus 3, go on, give me a number that's less than negative 3, any number.
Negative 5.
Okay, we sub negative 5 in, I get negative 5 plus 3 is negative 2. This comes back to the definition of absolute value. We said either it's A if A is positive, or negative A if A was negative. Well, we just end up with a negative answer. So it's going to be the negative of x plus 3. It doesn't matter which number I pick, I'm always going to get the negative of it. Well, let's ask the same question. 1 minus x, would that be negative or positive with our number? What was the number you picked again? Negative 5. So if we put negative 5 into that, we'd get 1 minus minus 5, which is positive. So this one would just be plus the other one. Add them together, and I'm drawing this line. But just for x is less than negative 3. The next issue here is at x equals 1, because that's when this one will become 0. So pick a number in between minus 3 and 1. Go on, pick a number between minus 3 and 1.
0.
Yes, that's the one to pick. It's always an easy number to sub in. So sub it into the first one. We get 0 plus 3 is 3. That's positive. So it'll just be the positive x plus 3. Sub it into the second one. 1 minus 0. That's also positive. Add them together. Okay, for this section I'm just going to be drawing the line y equals 4. That brings me to what happens when x is greater than 1. Any number you like bigger than 1. 5. 5 plus 3 is 8, so that's positive, x plus 3. 1 minus 5 is negative 4, so that's negative. I'm drawing the graph y equals 2x plus 2. So now I can draw the picture. At the point, it stops at the point negative 3, 4, but I've got the line y equals minus 2x minus 2. I then have the horizontal line y equals 4 until we get to x equals 1. And then after that point, I draw in 2x plus 2. And that's what that particular graph would look like. If you had to draw a subtraction, well, subtraction and addition really is the same thing. It's just that you're adding a negative number. So the way I think about it is not that I'm subtracting a graph, I'm actually adding the graph negative gx. And then I can just use the same idea. So here's, if I did x minus sine x, but the two graphs I've drawn there's y equals x, but I've drawn y equals negative sine x. So I'm just going to add these two together. Interesting thing to note here, when you've got y equals x plus some function, which is what I've got here, if that other function is bounded, which this one is, the sine curve's bounded between 1 and minus 1, then the new graph should be bounded by x plus the boundary, or plus the two boundaries. So the picture I end up with should be bounded by y equals x plus 1 and y equals x minus 1. They should become the boundaries of my curve. Let's see what happens. X-intercepts. Go on, there we go. Because when this does keep going, clearly these numbers are going to be bigger than here. We'll never get back to 0 again. The points I've added on are when the blue curve is 0. Well, if the blue curve's 0, I'm adding nothing to the red line, so I'm on the red line. So there's a lot more points along there. Pick as many points as you need. I've just got a couple. You'd end up with, it's not exactly a sine curve, because you'll see that the actual bump is not symmetric. It's sort of biased to one side of it, but it's still got that winding effect like a sine curve as it goes around the line y equals x, and it would obviously keep going all the way up that line. Multiplying graphs together then. Again, you would draw the two original graphs. So let's say I wanted to do x times e to the x. There's y equals x, and there's the exponential y equals e to the power of x. Going to multiply these two graphs together. X-intercepts become really important because now we're multiplying. When you multiply by 0, you get 0. So all the x-intercepts will become x-intercepts of the new curve. Well, on my graph there's only one there because the exponential has no x-intercepts, but y equals x has the 1. So I've just got 1 down there. Okay. All those x-intercepts, in our case we've only got 1, becomes like a boundary to our curve where the sign of the function will change. Remember, you can't get from positive to negative without going through 0. And so you look at each of the two functions and say, well, would it be positive or negative? So on the left-hand side here, the exponential is positive, but the line's negative. So it would be positive times negative, which is negative. I know I'm down there. On the right hand side I've got positive times positive, so I know, alright, the curve goes in that section there, so it gives me an idea this is where the curve goes. The y-intercept, well I've already marked it on this one because you only have one y-intercept, we've already found it, but that would be my next thing. Let's work out where it goes through the y-axis. Now these points are important, because when a function, or one of those functions is equal to 1, well if you multiply by 1, then you must be at the same point on the other function, because multiply 1 you get the same thing. Let's say this is the point 1, 1, so that's where 1 is on that one. So if I multiply it by the e to the x, I would end up on the curve. So I get 1 times the value. So I know I'm going through that point there. Of course the exponential is 1 at the y-intercept, so I end up at 0 there. Negative 1, same case, you just got to be careful, because with negative 1 it won't be actually on the curve because the sign would have changed, but it'll be the same distance but the other side of the axis, so maybe I've ended up, I guess, about there. If one of the curves approaches 0 or plus or minus infinity, so will the new function. Now what happens if only one of them does? See, over here on the right hand side, not an issue. They're both going off to infinity. So we know it's going to go to infinity, but have a look on the left hand side. The exponential is going towards 0 and the line is going to infinity. Well, 0 times infinity, what do you get? You look at the curve that what we call dominates, and that's the one you go with. Now, how do you tell if a curve dominates? It's the one that gets steeper or shallower the quickest, and that would be our exponential, because you can have a look at that compared to the line. The exponential is getting steep really quick, and also same with the shallowness of it. It gets shallow really quick. So whatever the exponential is doing, I will go with that. So it's going to approach 0. We end up with that sort of thing then. I've got to go through those points. I've said on the left hand side it's going towards 0, and on the right hand side we're going to keep going to infinity, and so that red curve becomes my new function, x times e to the x. Keep in mind, again, discontinuities can't magically become part of the domain of my new function. Symmetry, again, multiplication also retains symmetry. Let's try this one. We saw it before with polynomials. We've already seen a way of doing this. But here's another idea we could use. We could say, well, I'm going to be multiplying these 3 curves together, and I've drawn them on there. So the x-intercepts, wherever all those x-intercepts are, there's still going to be x-intercepts. Break it into regions. Positive times negative is positive. Then the next section, positive times negative is negative. Next one, positive times negative is negative. And then I've got positive times positive, which is positive. Okay, I end up with that sort of thing. Oh, it's hard to pick it up there, isn't it? Let's get rid of the purple. So that green one there, I end up with that. Now it looks like I'm just going flat there, but that's because of the scale of my diagram. It's coming down a little bit and then going back up again. We saw with polynomials, it will behave like the actual root itself, so I know it will inflect like the purple curve there. But yeah, it's another way we could look at it. Personally, I probably prefer the other way we did it with these ones. Okay, what about if you're squaring it then? You're multiplying a function by itself. Still multiplication. What happens is this. All your roots double, if you like. So single roots will become double roots. Double roots will become roots to the power of 4, and so on and so on. Here's random graph. There's my x-intercepts, but they will now all be double roots because they were single roots, they just cut it. Now they're all going to be double roots, so they're all going to turn like a parabola at those points. Every one of those stationary points, so the turning points, will still be stationary points. Yeah, the y value might change because you're squaring it, but at that x value, they'll still be the same. So we've got one up here. Look, it's a number bigger than 1. Square a number bigger than 1. It's going to get bigger. So I'll put it up there somewhere. Down here we've got to be careful because we're squaring a negative number. I've moved my scale from random curve the last time we looked at it to make it clearly this turning point is smaller than 1 in magnitude, and you square a number smaller than 1, it goes smaller. So it gets closer to the axis, but because it's now positive, because you're squaring it, it's actually on the other side, but it is closer. Okay, discontinuity is still going to remain. Horizontal or oblique asymptotes, just square their value. That's where it will go to. So on our one, this vertical asymptote, that's going to stay there. The horizontal asymptote, well, it was less than 1. Square a number less than 1, it gets smaller. That horizontal asymptote will come down. So about there I'll put it. Square a number bigger than 1, then the square is bigger than the original function. When it comes to drawing, what we're saying is I should draw the new curve above the old curve. It's going to be bigger. If it's less than 1, then when I square it, it's going to get smaller. So the new curve should go below the old curve. All right, what have we got? Well, 1 then becomes a key point. So let's plot those in. -1, it's going to stay there, but it's now going to be positive, so we'll flip it up a bit. So I know I'm going through those. Now I just got to go under and above. So here I am below 1, therefore it goes below the original curve. As soon as I pass 1, it must go above the original curve because it's getting bigger. So I'm going below, above. The next section, remember, is a turning point here. I'm looking at this bit here, a bit hard with the -1, but here, so I must go below, then above, above, then below, and we get our new curve. So there it is, the red one. That just leaves division. Well, just like subtraction is the same as addition, well, division really is the same as multiplication. You're just multiplying by a reciprocal. So the only difference then is our x-intercepts because of the bottom of the fraction problem. Those x-intercepts on the bottom of the fraction will become our vertical asymptotes, or maybe it's a point discontinuity depending on the curve. Start with this one, x plus 1, x minus 2 over x plus 2, x minus 1. So I have some x-intercepts, so x plus 1, x minus 2 will be x-intercepts, but the other two will become vertical asymptotes because they're on the bottom of the fraction. But it still breaks it up into sections. So I start at the very left, negative times negative times negative times negative. That's positive, and so on, and we get the sections. Right, that's where the curve's going. I know I've got to bend towards the asymptotes. I know I've got to go through those points. Y-intercept, let's work it out, and it ends up to be 1. So I've got to go through that point as well. Then have a look what's happening out at infinity. Again, if there's dominance happening, you know that's going to happen. Do you need to find your oblique horizontal asymptote? So on our one I could do that polynomial division. Yes, we got a horizontal asymptote at 1. I can find that. So let's draw that in. So another piece of information we have. And this all helps me draw my graph now. I end up with that. So I've got to bend towards the asymptote, go through those points, and there's my curve. Let's just, a bit hard to pick it up, so it's the darker blue of all those. This is an interesting one. I think this is the last one, but it is interesting. Sin x divided by x, what does it look like? Okay, there's y equals x, there's y equals sin x. Okay, there's all my x-intercepts. You'll notice I didn't put an x-intercept here because I'd be dividing by 0, which is not allowed. So I've either got a vertical asymptote or a point discontinuity. Now I have to do something here which you probably don't know yet. The limit as x approaches 0 is actually 1. Because what happens for very small angles, then we know that the angle is equal to the sine of the angle. And so this ends up being equal, so it's 1. It's what's called the small angle theorem. Let's say, not something you need to know right now, but it's useful for this picture. So what it means, I have a point discontinuity on this one, not a vertical asymptote. And when I do my regions, there we go, I'm going through all these, I end up with something like that. It's still got the windy thing, but because I'm dividing by bigger and bigger and bigger numbers, then the y value is getting smaller and smaller as you wind along. You'll notice it's an even function because sine x is odd, x is odd, odd divided by odd gives you an even function. So you have that symmetry going either way. Bingo. So yeah, keep that in mind with multiplying or dividing, because essentially the same thing. Odd times odd is even times even is even, odd times even is odd. Basically, same type of function multiplied together, you get an even function. Different types of functions multiplied together, you get an odd function. There we go, so just a handful of graphs to have a go at there.